All right, so last time we were talking, we discussed the fact that in finance, we had talked about a cost function that was linear. In other words, it had some amount of fixed cost that set our intercept, and then the total cost curve was the fixed cost plus the variable cost, and the line had a slope equal to the variable cost per unit. And what we then discussed was what's the marginal cost? So if we said, okay, the cost function is say 10 plus 2x or 2q or 2v or whatever, right? Where x is the quantity and y is the total cost. We'd start at 0 units, we'd have 10 y or 10 total cost. At 1 unit, we'd have 10, the fixed cost, plus 2, the variable cost. For 12, at 2 units, we'd have 14. At 3, at 6, right? Because 3 at 16 would be 10 plus 3 times 2, 16. And we said, what's the marginal cost? And what we said the marginal cost is what's the cost of making one more unit? And so when you have a linear cost function where the slope of the line is a fixed number, like 2 in this case, right? So the slope of that line, the slope of this line is 2. The marginal cost is always going to be 2, right? Every time we add one more unit, we're going to increase the total cost by a fixed amount, which is 2 every time. So that's the marginal cost. So we calculated that last time. And then we said, all right, if we draw our total cost curve, we start with our fixed cost. And then I said, reality is that if you try to increase your production by bringing in more resources in order to do it, because every time you increase your units of production, you're going to have to add, at a minimum, you're going to add some sort of supply cost, but also you're going to start passing through, as you try to bring in more resources, you are going to start to compete with other people in your marketplace for those same resources. And they may not even be doing something, say, in healthcare. They might be doing something in a completely different field, and yet they need the sum of the same resources you have. One of the most common resources, of course, is manpower, right? And so if you're working in, say, the Seacoast area, and you're looking for people who can do entry-level work like LNAs, we've talked about before, an LNA doesn't take that much training. It's a couple of weeks. If you're going full-time, it's a couple of weeks of training. And then boom, you're an LNA, and now you can go off and do LNA stuff, all the great things that LNAs do. Licensed nurse assistant, right? LNAs. But that same person could pretty easily also become a line cook at a restaurant, or a retail representative in a store. And they're going to bounce around between those kinds of jobs pretty regularly because it doesn't take much to switch between them. And so the supply elasticity of people in that labor market, in that side of the labor market, is quite elastic. It's elastic because it's easy to switch from one thing to another for those people, right? If you're basically content making, somewhere in that $18 to $20 an hour range, you're probably going to keep bouncing around. So if you hear, oh, hey, the restaurants are now paying 19, I'm making 18 an hour as an LNA. Hey, the restaurants are paying 19, quitting the LNA job, going to go become a line cook or a waitress or a dishwasher or whatever and make an extra buck. Then you hear, oh, hey, retail's now paying $20 an hour. All right, quitting the line cook job. I'm going to get a retail job. Oh, hey, LNAs have jumped up to 21, quitting the retail job, going over to LNA again, right? So that's the nature of that kind of work. But the thing is, because those people can move easily between roles, all of the employers are competing for them. And then it depends on how many people are in that market, how many people are willing to work those kinds of jobs. And today in COVID, we've had the great quitting, right? where everybody's kind of decided that they just assume stay home, or what really is happening, I think. What is really happening, I think, is a couple of things. One is older workers are just saying, screw this, I'm not doing it anymore. And then I think a lot of women with young children have left the labor market as well, because childcare has become more expensive. So I think we've lost those. And the problem is that the demand is relatively inelastic. And so when we have small changes in supply, it causes big changes in pricing. Anyway, so if you're there now and you're trying to push let's say you're running a nursing home and you want to increase your number of residents, you need more LNAs. Well, now you're competing with the restaurants in Portsmouth and Dover, right? Of course, you're competing with the hospitals that need LNAs. You're competing with other nursing homes that need LNAs, but you're also competing with other industries that will hire that same kind of labor as well, right? And oh, by the way, Sig Sauer down at, on Pease manufacturing, they pay even better. And so if they can get a job in there, they'll quit all of you and just go there, right? So, so as you start to compete, right, as the labor markets get tighter, the additional units of labor don't go up. The additional cost often does not follow a linear function. You now have to pay, if you want additional LNA hours, you can't just pay, one more LNA is not going to cost you $20 an hour. One more LNA is going to cost you $21 an hour or $22 an hour. And so what you see instead of a linear cost function is instead an exponential cost function, where the additional units, right, where the additional units past a certain point start costing you a lot more because you're competing and everybody's having to raise their prices because there's a shortage of labor, which is what's really happening right now. Is there is a shortage of labor. My daughter was working as a line cook in Portsmouth, and she was making $24 an hour, which is like absurd to me. Like, that's crazy money for a line cook, especially because prior to that, she'd worked as a line cook when she was in college, making like $15 an hour. Not that long ago, like 3 years ago, she was making $15 an hour. She's like making $10 an hour more as a line cook now than she did 3 or 4 years ago, right? Now she just got promoted to sous chef, which is like assistant chef. So we're very pleased. And now she's making even more than that. So kind of thinking to myself, if she starts making more than that, I'm going to have her get me a job, because, she's going to start making more than professors. Don't make a lot of money, by the way. That's like not a thing. So if you're like, I really want to make a lot of money, write off professor as like a potential career field. Okay. So reality is total cost functions tend not to be perfectly linear. Instead, they tend to be exponential, right? So if I graph, if you remember this from, from algebra, if I graph the function x squared, y equals x squared, what I'm going to see is a curve that looks like that, right? So if I then tag on some other function, some additional, stuff like a constant, say 100 and 10x plus x squared, I just wind up getting something that looks like this instead, where I have the 100 becomes my y-intercept, because what do? We set x equal to 0. That tells us where the y-intercept is, right? And then, that immediately starts, if you add the 10x function, it just gets fast. It just starts going up faster. But if you're graphing just x squared alone, what you get, that's what an exponential function looks like, is an upward curve with an increasing rate. Okay, so we're going to now, from here on out, we'll be using total cost functions that include an exponential component. Well, let me say, we might be using an exponential component. You'll need to ask, or you'll need to know, okay, does it have an exponential component or not? So when we do that, right, if we plug in an exponential component, our total cost is not going to move in a linear fashion. Instead, it's going to have this upwards curve. And so therefore, our marginal costs are not going to be equal each time. They're going to be increasing. So from, I didn't do that one. So we'll see, the first one will be 2, then it'll be 2.5, then it'll be 3, and, 3.7 and 4.8, and, so on. Okay, so that's what we're going to see. So I'm going to use a cost function, total cost function, 20,000 plus 10Q plus 0.075 Q squared. And I called this last term the kicker, right? So at a low number, that kicker term is not going to do much. But if we were to graph this at a volume of 0, at a Q of 0, what would our total cost intercept be? At a Q of 0, what's our total cost intercept? Molly, it's 20,000. How do you get it? Right. So when I say intercept, what I mean is, where does this function, where does the line that's described by this equation cross the total cost line, right? The y-axis. And so that would be at 20K, right? And then it would go up from there, and it's going to go up from there with a curve like so. Now, if I assume that my total revenue is, say, 100Q, right? Because I am in a market where my product is relatively undifferentiated, right? So last time we talked a bunch about commodities and how, you've got this really big market. So we'd have like we talked about like a global market for generic drugs of any sort, really, but generic ibuprofen, which is perhaps the most simple, generic drug. This would be the global market. We'd have our quantity global and our P global. And so if you were so the global supply and the global demand, the global supply is everybody in the world who makes ibuprofen or whatever the generic drug is we want to talk about, right? So that's the global supply. And that includes all of the factories in India, China, Bangladesh, New Jersey, right? Wherever they're being made. We add all that up together, and that creates the global supply. And then we have the global demand. Everybody in the world that wants to buy generic ibuprofen, which is pretty much everybody everywhere needs a little bit of ibuprofen every now and then, right? We used to call it vitamin M in the Army. It was kind of a joke because it's Motrin is the brand name, and basically the joke was, you get hurt, you come to see the PA, the battalion PA, and he gives you vitamin M, because it was pretty much like, anything wrong with you? All right, 800 milligrams of Motrin 3 times a day, and that's out the door almost always. That's mostly because it was a bunch of young guys and we were doing stupid stuff like falling down and, running too hard and doing, and so basically that was basically the right answer 90% of the time. The other answer was you're coming in on Monday morning and you are hungover and you're throwing up while you're trying to do the battalion run on Monday morning because it was Halloween last night. And so the other thing they give you is they bring you into the aid station and they stick you with a couple of liters of Ringer's lactate to rehydrate you. If you're hungover, there's nothing like a bag of Ringer's lactate and some Motrin. Takes you a long way to feeling better. Anyway, so we've got this global supply of Motrin or generic Motrin, ibuprofen, right? And if you are an individual producer, then the demand you're going to face is going to be the P global, right? And it's going to be a straight line where D is equal to P, right? Where your demand curve is a flat line and it's equal to the price that you're going to get per unit. And that price per unit is going to be whatever the global price is. Because if you try to sell your generic Motrin that you make for more than the global price, nobody's going to buy it from you. But at the same time, if you sell at the global price, you can sell as much as you can produce. You would never sell below P global, because why would you do that, right? Like, let's say the global market price is $2 a bottle. Why would you ever try to sell your thing for less than $2 a bottle if you can always get $2 a bottle, right? You'd just be losing money from the get-go. So you wouldn't do that. So if P global is 2, right, you'll always sell it at 2. And you're able to sell, because there's such a huge market. If you make 100 bottles, 1,000 bottles, 100,000 bottles, 1,000,000 bottles, you can sell them into the global market at 2. So however much you can produce, you can sell at 2. That's what that line, that horizontal line where D is equal to P, that's what that means, is you have an infinite amount of demand for the product that you can make, right? So then it just comes down to, what is your supply curve? What is your supply function? And your supply function is going to be equal to your marginal cost. And oh, by the way, let me back up for a second. If I can sell 1 unit at, say, 2, I can sell 2 units at 2, 3 units at 2, 4 units at 2, 10,000 at 2 each, right? Or in other words, I can sell 1 unit for $2, 2 units for $4, 10 units for $20. What's my marginal revenue? What's the additional revenue I get from selling 1 more unit? So if I can sell 1 and I get 2, 2 and I get 4, 3 and I get 6, 4 and I get 8, ... 10,000 and I get 20,000. What is my marginal revenue? Got it? No, okay. Allie, what do you think? What's my marginal revenue? How much more do I get from selling 1 more unit? 2. Does it change? It doesn't, right? Because going from 1 to 2, I get +2. Going from 2 to 3, +2. From 3 to 4, +2. From 10,000 to 10,001, I get 20,002, +2. Right? So this is an example of where you are selling into a competitive market, where you are selling a product that is fundamentally a commodity. Your marginal revenue is going to equal the price. When you are in a perfectly, this is called this technically is a perfectly competitive market. There are relatively speaking, relatively few of these circumstances. Things like generic Motrin are pretty close to a perfectly competitive market. There's such an enormous demand, and there's so many suppliers that nobody can manipulate the price of the market. And so everybody faces a demand that's based on the global price. And so the demand is equal to the global price, which is equal to the marginal revenue, which we're saying in this case is, say, $2, right? So all three of those things are $2. The demand equals the price equals the marginal revenue. This is unique to the perfectly competitive market. So oil producers face this, corn producers face this, gold producers face this, and some limited subset of the medical industry faces this. Probably more along the lines of like people who are producing the raw materials that are used by medical producers are definitely in this zone, right? So people who are selling medical gases, for example. So like you run a hospital, you have to buy canisters of oxygen, you have to buy canisters of, you know, whatever the various gases are, nitrous oxide. And there's going to be a global market because, first of all, it's easy to move that stuff around. Once you've got it refined, it's easy to stick it in a tank and put it on a train and send it wherever it needs to go. So the market for things like medical gases is pretty close to perfectly competitive. Not perfect, but pretty close. So if we take this fact that if we are in a perfectly competitive market where our revenue, where our demand equals price equals marginal revenue, and we produce, you know, a quantity of 10,000, what is our total revenue going to be? Well, if total revenue is price times quantity, what's my total revenue going to be? Working with a $2 price, 20,000, right? $2 price, right? All along here is $2, and I'm going to sell 10,000 of it. My total revenue is going to be 20,000, right? If I did 20,000 units, it would be 20,000 times 2, 40,000, right? It's not particularly interesting, but the way you know how much your total revenue is you're just calculating the area of this rectangle, right? It is 2 high and 10,000 wide. All right. So then if we decide to graph that as total revenue versus quantity, we get the same thing as we learned in finance, where we're facing a fixed revenue per unit, where the slope of the total revenue curve is equal to the price, right? Where if we do 1, we get 2. If we do 2, we get 4. If we get 3, we get 6, and so on, all the way out. That gives us a linear total revenue curve where the slope is equal to the price. In the next chapter, we'll start talking about monopoly and where monopolists don't face a global price. They set their own price. They're able to set their price, and we'll then have a curved total revenue function. Sorry, it's actually like this, right? We'll have a curved total revenue function. But for now, we're going to have a linear total revenue function. All right. So let's assume we're fundamentally working in a environment where we are price takers, which means that we can't set our price. We have to accept whatever the market price is. And so the market price is 100. So if I'm going to graph, I've now graphed my cost function, my total cost function. Right. If I want to put my total revenue function on the same curve, on the same graph, what's the line going to look like for total revenue? So I've got the equation, it's 100Q. So if Q is 0, what's total revenue? 0, right? So the total revenue function is going to start here at 0. And what's that line going to do? I'm going to draw this line, this total revenue line. Is it going to go up or down? It's a positive number, right? So if I get 1, how much total revenue do I have? 100, right? If I get 2, I get 200. If I do 3, I get 300. So what's happening? It's going up by how much each time? 100. Its marginal revenue, therefore, is 100, right? Because if I do one more, if I sell one more, I get an additional $100. All right. So if I'm going to graph that, it'll probably look something like this. It's going to start going up in a straight line. It's going to take a while for it to get up to the total cost curve because the total cost curve starts at 20,000. So we know it's starting well below the total cost curve because I've got to sell enough to cover the fixed cost, right? Which means I've got to sell 200, right? In order to just cover the fixed costs, never mind the variable costs. So I'm starting well below, but at some point, what's likely to happen is I'll catch up early on with the cost curve. Because the total revenue is going up at 100, right? This got a slope of 100. That's a pretty fast rising line. And this one's got a slope initially of only about, this number is so small at a small quantity, like at a quantity of 1, we're talking about 7.5 cents, right? So that's not much of an impact. Even, it does go up fairly quickly once that Q starts coming into play, but the initial impact is just 10, which is not a lot. And so it's possible for the total revenue curve to catch up pretty quickly with the total cost curve. And when the total revenue curve crosses the total cost curve, so at a point, say, at any point, say to the, let's call that Q1, at any point to the right of Q1, the total revenue curve, if I draw a line straight up to say Q2, the total revenue curve is above the total cost curve. And so that means I have total revenue that's greater than total cost, which means I have a profit, right? I'm making a profit because my total revenues are greater than my total costs. And so I've got money left over. I brought money in, I spent some money to make that money, but I didn't spend all of my money that I brought in. So I've got extra money left over. That's my profit, right? So what is Q1, this point here, where the total revenue line crosses the total cost line for the first time? Is it? Break even, right? That's my break even point. Now, I keep going. If I'm just barely, let's say like whatever Q1 is, if I'm 1 unit over to the right, I'm making a little bit of profit. As I keep going, I'm making more profit, right? Because this gap is getting wider. So you can see it, like the gap here is not as wide as the gap here, right? The gap between this line, because of this curve, the gap here is actually wider than the gap here. And then past that point, let's call that Q3. The lines start to come back together again. So there's some point, it might not be exactly right there, but roughly there's some point in here where the gap widens to its widest point and then it begins to come, you can see it comes, it opens up, and then it closes back down again, right? So there's some point here where the gap is widest, and then it begins to, and then the gap begins to shrink until we get here. Let's call that Q4. When we get to Q4, we have another break-even point, right? But this is not a happy break-even point. Because after Q4, what happens? If I draw a line up, now the point on the total cost curve where that line crosses is now above the total revenue curve, which means we're spending more money to make the things than we are bringing in, right? So we have a loss. So our zone of profit is between the two break-evens, and to the left is loss, and to the right is loss. So there's this zone we want to be in, somewhere between Q1 and Q4, which are the two break-even points, right? We want to be somewhere in between there. And if the gap between the lines represents our profit, where do we want to be in terms of that gap? The quantity that generates that gap, right? So there's different quantities as we roll along. It's getting bigger and bigger until we get to, let's say, Q3, where it's the widest. And then as we move to the right of Q3, it starts getting smaller again. What quantity would you want to produce at? Molly. Right. Why? That's right. That the wider that gap is in that zone of profit, the wider that gap is, the more your profit you're making. Because in between Q1 and Q4, right, is our zone of profit. Between where the total revenue curve crosses the total cost curve the first time, and the total revenue curve crosses the total cost curve the second time. In there is my profit zone. Just as at the break-even point, I'm making zero profit. Total cost is equal to total revenue. Out here at Q4, total cost is equal to total revenue again. I'm also making zero profit. So as I move to the right from Q1 towards Q3, assuming that Q3 represents the widest point, I'm getting more and more profit. And then when I hit Q3, I start to see that profit start to shrink. So the ideal point that I want to be at is the point where the gap is widest, because that's where I get the most profit. Does that all make intuitive sense when you look at the graph? I want the widest point. What do you think, Allie? Does it make sense or no?
Yeah. No.
Thank you for asking that question, because that is what we're going to talk about next. Okay, I'll have your check for you later. All right, so there is a trick to figuring this out, okay? And that trick is I want to find, so the slope of this line, the slope of the total cost line is not fixed, right? If I look down here, if I didn't have the kicker term, you'd tell me the slope was what? Assume this isn't here. The slope of the total cost curve would be what? Unrich? 10, right? Because it's going to go up at 10 for every unit. Assuming that's not there, right? It's going to go up for 10 units. But unfortunately for you, it is in fact there, right? So now it changes the nature of the line. Without that, we'd have a straight line going up from total cost at 10. And then we'd have the kind of problem we did in finance, where we could say, okay, we have one break-even point, and we just want to be to the right of that break-even point. However, when you have exponential costs, you're going to have this funky curving line that goes up as you go out. You're competing for more resources. That causes your costs to go up at an exponential rate. That is a more realistic cost function than a linear cost function. So The problem here is that the slope of this line is constantly changing because this kicker term is growing. So there is no one slope. It is a constantly changing slope. Whereas the total revenue line, the slope is 100. It's always 100. Wherever you are, it's always 100. Because we're in a competitive environment, we can sell as much as we want. So that slope is always 100. Because we're in a global market where we're selling our bottles of ibuprofen or canisters of nitrous oxide or whatever it is for $100 per unit. Right? Maybe we could imagine we're selling cases of ibuprofen at $100 a unit. Right? 50 cases of 50 bottles. They're each worth 2, but we're selling them in units of 50, so that's why they're 100. Okay. But what we know is as we go out, we're going to run into problems where we have to hire more people. And then we're starting to compete, for our manufacturing line. Now we're competing with Sig Sauer. And oh, by the way, they want to tap into the same manpower pool as we do. And so we're now into a competitive situation where we're bidding each other's labor costs up. And that's what causes this curve to jump up. So what we need to know, I'm just going to kind of try to explain this. What we want to know in order to find this point where the widest point is, we want to find where the slope of the total cost curve is equal to the slope of the total revenue curve. And so I'm drawing that line against that curve. Does anybody know what that line is called? That red line I just drew? Somebody other than Molly? Does anybody know? All right. It's the tangent line. So if I have a curve, imagine I can't do that. Let's get a video. Imagine this is my basketball, right? Or any kind of ball, whatever ball you want to choose. It's a circle. I can put a ruler on top of the ball. And assuming that the ball is perfectly flat. Assuming the ruler is perfectly flat and the ball is perfectly round. If I take and I put a ruler, I bring the ruler and I'm like, all right, I'm going to put it on top of the ball. It's only going to touch the ball in one spot. Now I could rotate the ruler around and holding it against the ball over here, it'll still only touch it in one spot, right? Unless you bend the ruler, but we're not going to do that. If I bring the ruler over here, it's only going to touch it in one spot. These are called tangent lines. So these rulers that we're putting against the ball touch the ball in one spot. So any sort of curve that we have, we can draw a tangent line to it. An infinite number of them. We can draw another one right here that goes like this, right? And we can just keep filling in as we go around. Each point on that circle is going to have a unique tangent line that's associated with it. It'll be completely different than every other tangent line. Okay. So when I have a curve, misfire. When I have a curve like so, I can draw tangent lines along the curve that touch the curve in only one spot. Each of those tangent lines is a unique line that touches the curve in only one spot. And if you were to calculate the slope of each of the, sorry about this one is crooked. I could calculate the slope of each of these lines, right? So let's call this one A, B, and C. If I calculated the slopes of each of those lines, would the slope of B be steeper, meaning a bigger number, than A? So if I take away the curve, what I'm drawing then is, here's A, here's B, here's C, 3 lines, right? You should be able to look at that just visually, I'm taking away the curve now, just look at those and you tell me, yes, A has this flattest slope, B has a slope close to 1, and C would have something greater than 1 because it's going up faster than 1 to 1. A is probably something less than 1. B is something probably close to 1 because it's almost at a 45-degree angle. And then C is clearly more like a, 80-degree angle, something like that, right? It's going up really fast. So A is a flatter slope, B is about 1, and C is something greater than 1. So now I'm looking at this curve. At point A, the slope of the curve is whatever the slope of line A is. At point B, the slope of the curve is whatever the slope of line B is. And at point C, the slope of the curve is whatever it is at point C. Think about this. You're in your parents' Tesla, right? And Teslas have this amazing takeoff, like, right, they just spin out. Like it used to be, we used to talk about, like, if you could do 0 to 60 in like 5 seconds, that was like a Lamborghini. It was an incredibly fast car. But now Teslas can go like 0 to 60 in like 3 seconds. It's like a crazy faster because there's no gears, there's no mechanical stuff happening. It's just you hit the accelerator and it, the motor just goes. And so they have this incredible acceleration. But if you're sitting at a stop sign, your speed is 0, right? So at 0 seconds, so this is seconds, right? You start at 0 and then you go up really fast, and then you probably level out like this because then the cops are coming, right? So this is your speed. So at second 1, you're probably going, 0 to 10. And then in second 2, you're up to 30. And then at second 3, you're up to 50, right? And it's say second 3.5, you're at 60 or whatever it is. Like here, now you're here. Let's just say 4. Right now you're at 60. What's your acceleration during time, during the first second? So my speed is, right? Speed is different than acceleration, right? My speed at any given time, I just look at my my speedometer. I look at my speedometer and it tells me, right? The line is at 40. Okay, my speed is 40. I accelerate a little more. My speed is now 50 and I'm cruising at 50, right? Get out on Route 16, I'm driving out towards Portsmouth, and even though the speed limit's 55, everybody's going 70. So I bring up my speed to 70 and I'm cruising at 70. If I hit 70, what's my acceleration? I'm sitting at 70. What's my acceleration at 70 miles an hour? It's 0, right? The acceleration is how fast it's changing, right? Not what the speed is. So if I'm cruising here at 70, let's say this is 70. My acceleration is 0. So if I have a curve that comes up and then goes flat, like this, that has a slope of 0. It's not changing, right? It's not changing. It has a slope of 0. So it's fixed at 70. So if I was to write an equation for this point, it would be y equals 70 or s equals 70 in case of, if this is s or speed. But when I go from at 1 second, so from 0 to 1, I've got some acceleration because at 0 I was doing nothing, and at 1 I'm now doing 10 miles an hour. So I'm accelerating from 0 to 10, right? There's acceleration during that first second. And then there's more acceleration during the second, more during the third second, more during the fourth second, and then a little more during the, let's say the fifth second, but then I slow down. So the slope of the line at any given point is the amount of acceleration that I have going in. So from 0 to 1, my acceleration is 10. From 1 to 2, my acceleration is 20. You get it? So like from 0 to 1, I go from 0 to 10. So at the end of second 1, I'm now at 10. So my acceleration in the first second from 0 to 1 was 10 miles an hour. From 1 to 2 seconds, my acceleration goes from 10 to 30, that's 20. From 3 to 4, I go from 50 to 60, which is actually a slower acceleration rate than it was from 3 to 4, right? So what did I say? 3 to 4, from 2 to 3. From 2 to 3, I'm doing, in that 1 second, I make 20 miles an hour of acceleration. From 3 to 4, I'm only going 10 additional miles of acceleration again. I'm actually I'm slowing down my acceleration. So like anybody guys ridden in a Tesla where somebody's trying to show off and they like hit it to the floor and you go, you get pushed into your seat? Yes? No? Okay. So you know what I'm talking about. Or even just, in your old jalopy, and if you hit the, metal, the pedal to the metal, you'll get a little bit of pushback as you kind of accelerate, right? So like in the minivan, the adventure van, it actually has my 2004 minivan has a 300 horsepower engine, which is a huge engine. And you know what? It's 18 years old, but it'll still take off. I can still lay rubber in my minivan. It is the coolest little car. Anyway, it's not little, but so my point here is what we've got is some amount of speed, but if you want to talk about acceleration, that's different than speed, right? Acceleration is the amount of change over a given period. The tangent point on this curve. So if I was to draw a tangent point right here, and then another one right here, and another one here, what you can see is steep, steeper, getting flat, going flatter. The tangents represent what we'd call the instantaneous acceleration. So rather than thinking about it as over a period of 0 to 1 or 1 to 2, we're now thinking of it at the 2-second point. How much acceleration are you experiencing? At the 3-second point, how much acceleration are you experiencing? So those tangents tell you what we call the instantaneous rate of change, or the instantaneous, in this case, acceleration. But if we're talking about costs, the tangent of the total cost curve is the rate at which the cost is increasing. So if I drew a tangent curve of the point, say here, it's hard to do because it's almost flat. Let's say I draw a tangent. Let me redraw this so I don't have to mess this one up. I've got my total cost curve. I pick a point here. My tangent's like that. I pick a point here. My tangent's like that. What you can see is it's getting steeper, right? The slope of each of those tangent points is getting steeper. What that means is the cost is accelerating faster and faster. So unlike our Tesla that eventually slows down at 70 miles an hour, this just keeps on getting faster and faster and faster. So each unit, it's like more like a rocket ship instead of a Tesla, right? It's gonna keep on getting faster and faster. So this gives us our instantaneous rate of change. Okay. What we're looking for to find the maximum gap between these two lines, what we're looking for is the tangent point of the total cost curve that is parallel to the total revenue curve. So in other words, if the total revenue curve has a slope of 100, I'm looking for a tangent point, tangent line that also has a slope of 100. What happens here geometrically is at that point where the tangent of the curve matches the slope of the line of the total revenue curve, that gets us our point of maximum profit. That gets us our point where the two lines are the farthest apart. Aren't you glad you asked? So what we have to find is, how do we figure out where on this line the tangent is equal to the total revenue? So in order to do that, we've got a little procedure we're going to do. We're going to try to calculate, because the slope, well, so let me pause for a second. The slope of the total revenue curve we said is 100. And that is also equal to the marginal revenue, right? One more unit of, if we sell one more unit, we'll get $100 more. That is the marginal revenue. So this curve, the marginal revenue for this total revenue function is 100. We have to figure out how to get the marginal cost for this curve. If this curve didn't have that kicker term, the marginal cost would be how much? Remember, marginal cost is the cost of doing one more. So if you pick any arbitrary Q and then add one to it, so if you go from 100Q to 101Q, how much additional cost would you generate using this cost function? 10, right? It's the slope of the cost curve. But if I add that, then like all bets are off. We can't say that without doing some calculations. Okay, so same with the total revenue curve, right? The total revenue curve for this chapter is always going to be pretty straightforward. It's 100Q. So let's talk about the total revenue curve first, and then we'll talk about and how to mathematically get the marginal revenue. So you can just look at this one and say, if I said the slope of the line's 100Q, what's the marginal revenue? You don't really have to do anything. All you just say is it's 100. Whatever the constant is that's being multiplied times the variable, right? Whatever the coefficient is, that the 100 is the coefficient. Whatever the coefficient is, that's the marginal revenue, right? So if you've got a total cost curve that's 20Q, the marginal cost is 20. Let's talk about the math of it. All right. I want to get to the marginal revenue. Anything to the anything to the first power is itself. Okay. What does 10 to the first mean? It means 10. What does 10 squared mean? It means 10 times 10, right? Ten cubed is equal to 10 times 10 times 10. What is 10 to the 0? What is it? No. 1. Anything to the 0 power is 1. You need to memorize that if you don't. So you need to remember that. Anything to the 0 power is 1. Anything. A bazillion raised to the 0 power is 1. 47 raised to the 0 power is 1. Right. Q raised to the 0 power is 1. x raised to the 0 power is 1. Anything raised to the 0 power is 1. Okay. Anything by itself it is itself raised to the first power. So if you just see the number 10, it's technically 10 to the first power. If you see the number 472, it's technically 472 to the first power. Whatever, anything raised to the first, anything sitting by itself is just itself raised to the first power. So those are two rules you need to remember for this, what we're going to do from here, for the next several chapters. Anything raised to the 0 power is 1. Anything sitting there by itself is technically raised to the first power. We don't usually write it because it's kind of redundant. It's like saying, 472 times 1. Well, duh, it's still 472. Like, it doesn't matter. 472 to the first power is also just itself. So if I know that anything sitting there by itself is itself raised to the first power, what can I say about this Q? It's actually Q to the 1, right? All right. So if I got Q to the 1, what I'm going to do, I'm just going to ask you to memorize this process because there really isn't any, because I don't want to spend the next 5 weeks working through it. I'm going to ask you to memorize this process. This is called the power rule. Okay? Power rule. I want to find the marginal revenue. What I'm going to do is I'm going to take the exponent and I'm going to bring it down here and put it in the first term. Then I'm going to bring the coefficient down. Then I'm going to bring the variable down. And I'm going to subtract 1 from its exponent. So 3 things happened. I took the exponent and I brought it down in front. I brought the coefficient down. Then I took the variable and brought it down and subtracted 1 from the exponent. Okay. So Q to the 1 what's 1 minus 1? 0, right? So now we have Q to the 0. What is Q to the 0? We just said it's 1. So simplifying this mess, we have 1 times 100 times 1. 1 times 100 is 100, times 1 is 100. So there we go. You've got the marginal revenue is equal to 100. Okay. Pretty straightforward. Now, you already had the intuition that the marginal revenue was 100. So you don't need to do all this if you're looking at it and the variable is raised to the first power. So that is, let's do another one. Total revenue equals 20 to the 20Q. What do I know? Q is sitting there as itself, so it is actually Q to the 1. I want the marginal revenue. I grab the 1, bring it down. Then I grab the coefficient and I bring it down. Then I bring down the variable, but I subtract 1 from its exponent. So then I know I've got Q to the 0. So I have 1 times 20 times Q to the 0, which is actually 1. So that means 1 times 20 times 1 is 20. So the marginal revenue is 20. And you could have just looked at that and told me that because you already know that. Right? You know that if my total revenue function is 20Q, then if I add one more Q, one more unit of quantity, I'm going to get $20 more. All right. What about my total cost? What if my total cost is 10Q? Well, intuitively, you know it's going to be what? 10, because it's, but humor me. The marginal cost then is going to be, that's actually 1. Bring the 1 down, bring the 10 down, and bring Q to the 1 minus 1. So I've got 1 times 10 times 1, which is 10. All right. But we didn't have, total cost function was 20,000 plus 10Q. Here's our new rule that you're going to use. Any constant without a variable goes to what? Who knows the answer? 0. Any constant that's sitting by itself without a Q goes to 0. So under the power rule, the 20,000 becomes 0. Then we do the 1, right? 10, Q to the 1 minus 1. And that gives us 1 times 10 times 1, or 10. So when my cost function, my total cost function is 10Q, or total cost of 20,000 plus 10Q, the marginal cost is the same. Now, that seems like, why? Wait a minute, that's crazy, right? But we're focused on the additional cost of adding 1 more unit. So if I have 100 units at 10, for that total cost equals 10Q, or total cost equals 20,000 plus 10Q. Well, if I plug 100 in for Q, what do I get? 10 times 100 is 1,000. And 101 times 10 is just add a 0 to the end, right? Anything times 10, you just add a 0 on. So 101 times 10, add a 0 on to 101, you get 1,010. Over here, at 100, I get 100 goes in here, that's 1,000, plus 20,000, that's 21,000. 101 is 10 times 101, which you already know is 1,010. So it's 21,010. What's the marginal cost? 1,010 minus 1,000, 10. 21,010 minus 21,000, 10. So even though maybe your gut intuition is like, no, it can't possibly be the same marginal cost, remember what we're actually talking about is the change of 1 more, not the overall total cost, but how much additional cost, the marginal revenue or the marginal cost is how much more revenue do I get from doing 1 more, or how much more cost do I get from doing 1 more, not what's my total. It's the difference. It's the acceleration, right? As opposed to the actual total. All right. So that's rule number 2, is any constant goes to 0. Any constant sitting by itself being added to something else is going to go to 0. Now, let's deal with the actual function we were dealing with a minute ago. We have total cost equals 20,000 plus 10Q plus 0.075 Q squared. All right. What's the marginal cost? Well, we have 20,000 sitting by itself. It's a constant. It has no variable associated with it. So it goes to 0. Then we have 10Q. So that's technically 10Q to the 1. The 1 comes down. Then the 10 comes down. Then we get Q to the 1 minus 1. Right? So that's 0. We can ignore that now. 1 times 10, Q to the 1 minus 1 is 1. Q to the 0, right? Anything to the 0 is 1. So that gives us 10. All right. What do we do with anything that's bigger than a exponent of 1? We do the exact same thing. Okay. So we do the exact same thing as we did with 1. So what do? We take the 2. We bring it down in front. Then we grab the constant. Then we bring down the variable, write the original exponent, and subtract 1. So that's 2 times 0.075 times Q to the 1, which is just Q, right? So 2 times 0.075 is 0.15. So we get 10 plus 2 times 0.075, 0.15 times Q. Can you guys do this? We'll do a couple more, but it's not complicated, right? Like it's a couple of steps to memorize, but it isn't like I'm not doing some weird voodoo up here. I'm just following a sequence of steps every time. Same steps. Good. Congratulations, you just done Calc 1. Right. That's basically everything that you do in Calc 1. So this is calculus. I didn't want to scare you by saying it before we started, but this is calculus. This is called the power rule. It comes out of calculus. It's just a mechanical process, nothing to be scared of. Okay, so let's do another one. It's the same sheet. Let's assume total cost is 5,000 plus 100Q plus 1/5 Q squared. Because I know most of you hate fractions, so I'm going to throw one in there. Feel free to convert, right? 1/5 is 0.2. So if you don't want to do fractions, change it. All right. I want the marginal cost, 5,000. It's a constant. What does that go to? 0. 100Q is technically right. So it's 100 to the 1. So I'm going to bring down the 1. I'm going to stick with I want you to keep doing the process the first few times, right? Feel free to jump once you feel like you've got this locked in. You can just be like, yeah, I don't need to do all the lines and the drawing and the doodles, right? Then I bring down the 100. Then I bring down the Q to the 1 minus 1, right? And so that is, I don't even need the plus. 1 times 100, Q to the 1 minus 1 is Q to the 0. Q to the 0 is 1. So 1 times 100 times 1 is 100. Which is what Hannah said. All right. Now, I bring the 2 down. I bring the constant down. I bring the Q down to the 2 minus 1. So I got 2 times 1/5 is 2/5 or 0.4, 0.2 times 2 is 0.4. Times q to the 2 minus 1 is q to the 1, which is just q. So 5,000 plus 100q plus 1/5 q squared. The marginal cost is 100 plus 2/5 q. All right, let's do another one. Total cost is 500 plus 3q plus 1/8 q squared. Now you do it. I'm not going to talk. And if you're comfortable, you can skip the stuff on the where the q is to the first power. But I would encourage you, especially where the exponents are greater than 1, to do the little process that I did. Because trust me, I do it. I still do it. I've been doing this for years and I still do that. Just to keep myself from screwing it up. How many of you guys have had calculus? No? Okay. Anybody? Anybody willing to admit that they had calculus? Okay, you had it? Okay. Okay. Oh, right. All right. All right. So if you took calculus, you do all these limit theories and stuff, and it's just a lot of stuff. And then all of a sudden they're like, you know, and you do all this math and you get this result that what we just got. And then like 5 weeks in, after you've done all this crazy math with all these deltas and things, they're like, yeah, so here's the cheat. You just do the power rule. It's this boop, 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 boop. And you're like, what have you done to us for the last 5 weeks? So, all right, what do we get? 500 becomes 0. 3q becomes 3, right? Because that's q to the 1. You bring the 1 down times 3. Q to the 1 minus 1 is q to the 0. Q to the 0 is 1. So that's 1 times 3 times 1. All right. Then we bring the 2 down times 1/8 times q to the 2 minus 1, right? Becomes 3 plus 2 times 1/8 is 2/8, which is the same thing as 1/4, times q to the 2 minus 1, which is q to the 1, which is really just q. You all are going to quit HMP and go over to the math department. I know it now. You're loving this. I can see it in your eyes. Or Jasmine's trying to keep her eyes open. But that's because she's got it so in. She's closing her eyes because she's feeling the mathematical spirituality of the power rule. She's moving up to nirvana in class as we speak. She's about to shoot off into another plane of existence. Okay. So you now know how to do both marginal cost and marginal revenue. So here's what I'm going to tell you. What's the marginal revenue for the total revenue curve? With a slope of 100, it is 100, right? Because it's going up by 100 every time you add a Q. What we're looking for is the marginal cost that's going to be equal to the marginal revenue. So to find the profit maximizing quantity, find that number that Ali was looking for half an hour ago, right? We want to find where the marginal cost, which gives us this tangent line to the total cost function. We want to find where the marginal cost is equal to the marginal revenue. That will give us a tangent line that's equal to 100. So what we have to do to find profit maximizing quantity. Set marginal revenue equal to marginal cost. I want you to memorize that. Staple it to your forehead. Tell people at Scorps this weekend or tonight when you go out trick-or-treating that, you know what? To find the profit maximizing quantity, you set marginal revenue equal to marginal cost. And people are like, that is so cool. You are cool. I want to be your friend. All right. So what do we say? We have, so we need marginal revenue equal to marginal cost. We've got total revenue is equal to 100Q. That means the marginal revenue is equal to, well, we're going to take the 1 down in front. 1 times 100 times Q to the 1 minus 1 is Q, 1 times 100 times 1. So the marginal revenue is, thank you. I'm looking at Tess. All right, we know that. And then we just worked through moments ago. And we can do it again just because it's so much fun. The marginal cost, right? 20,000 goes to 0. 10Q goes to 10. Then we get 2 times 0.75. That's 0.15. Q to the 2 minus 1, which is Q to the 1, which is just Q. Thank you, Tess. All right, now I'm going to set marginal revenue equal to marginal cost. Well, if the marginal revenue is 100 and the marginal cost is 10 plus 0.15 Q, how we can get our answer. I'm going to subtract 10 from both sides. 90 equals 0.15 Q. Then I'm going to divide through by 0.15 and 0.15. That cancels, and I have 90 divided by 0.15, 600. So Q equals 600. So the answer to Ali's question is Q3 is equal to 600. All right, so Q3 is equal to 600. So we will look at, we didn't get to the Excel sheet, but the Excel sheet runs through all these calculations. So we'll do that next time. We'll look at some graphs and we'll put this one to bed and we'll see if we can go on to chapter 12.